So we just have learned last time that using or not using the video sharing and not for all these online meetings and not using high definition saves 6% of the call usage of the USA. That's an incredible amount. Eh? So what I will do is, after I have introduced you, I will turn off my video, just since it's a sustainability lecture. Oh, but I think it's almost a bit, not so nice, but you speak to the screen. Ladies and gentlemen, I welcome you all to our lecture, Sustainability in Computer Science. I'm very happy to have our speaker today, Nysret Musliu, here. Nysret is running the Christian Doppler, you can read it, Laboratory for Artificial Intelligence and Optimization for Planning and Scheduling. And I guess in his presentation, he will tell us how much this has to do with sustainability and reducing waste on all different levels. I'm just coming from the Senate meeting of our university, and sustainability was a huge issue for the new rectorate we have now since beginning of 1st of October. And I was very proud when I said in front of all the people, I have to leave now because I have to moderate our lecture on sustainability in computer science. So Nysret, thank you for having you, and it's your floor.
Yeah, well, thank you very much for the introduction. So yeah, as you said, I will speak today mainly about some application which we have in Christian Doppler laboratory, and in general try to give some overview about AI and optimization for some sustainable applications. Of course, AI and optimization, both fields are very wide, so it's impossible to give all the information, but I will try to give some examples so that you have at least a few applications where AI and optimization techniques are used very successfully. So regarding my talk, first I will talk about several applications which involve different kind of resources and energy and so on, and which are important for sustainability. And those applications are in domain of employees planning and scheduling, production planning and scheduling. Then I will speak a bit about a project we have about food waste reduction. And then we'll give some overview regarding the use of AI and optimization techniques for this kind of problems, where I will just mention a few important things for those kind of applications, like modeling, exact techniques or heuristics, hybrid techniques, and so on, and also the use of machine learning for this kind of applications. So my presentation today will be more about using of computer science or techniques from computer science for sustainable applications. But as I will show later on, also algorithm selections and so on, some of the techniques can also be used to select the right optimization technique so that you don't run too much the algorithms and so on. So you can spend also there, of course, energy. Yeah, so those are the different applications which have been considered or investigated in our not only CD Lab, but also in the previous publications. You see here a lot of applications from personal scheduling, planning, then production scheduling and planning too. You see also some classical combinatorial optimization problems like TSP and vehicle routing, and also some educational timetabling problems. And I will talk about 2-3 problems from those from the list of problems which are listed here, and show to you why good techniques for this kind of applications are important. So of course we have some connections now. All those applications, or most of them, have some connections to the sustainable development goals of United Nations. And typically the applications which we have been considering are important for SDG 12, for example, responsible consumption and production, Then if you want to reduce energy in some applications, for example, in production scheduling and so on, then the SDG 7 would apply here. But we have also applications in personal scheduling, where the well-being of employees is very important. And I will show also in the next slides some applications in which you can see how the techniques were applied to solve different kind of personal planning and scheduling problems. Okay, so let me start first with the first applications, which is in the domain of employee scheduling, which looks in the first moment maybe a very simple application, but is not really simple applications. It's also very, very important in different areas, because the work schedules will influence the life of employees. So it's very important to have a good timetables or schedules for employees, especially for employees who work in 3 shifts or in night shift and so on, because there are different studies from medicine, from psychology and so on, that such timetables have enormous impact on health, social life, and motivation at work for the employees. In other side, of course, the organizations, the companies, and public sector and so on needs to meet the workforce requirements, so that they can assure the quality of their services and operations. So what you have typically in those cases, it's you want to find solutions which in a way satisfy all parts here, which are listed in this slide. Where do those applications appear? So especially in organizations or companies and so on, where you have a fluctuation of the workforce, and for example, airports, call centers, air traffic control, of course, hospitals, public transportation, then production plants and so on. So there are a lot of applications where shift work is also important, and you need this kind of good schedules for the employees. And like I said, you have different stakeholders here. You have the employees who would like to have free days in some days, who, of course, for whom we want to have a good schedules because of their health and social life and so on. Then, of course, each state has a labor laws which allow something and don't allow something. For example, too many shifts, night shifts in a row, and so on. And then you have the companies who have their interests. So the aim here in optimization is to find schedules which, like I said, fulfill different constraints, and especially are good for the well-being of employees, which is a very, very important criteria in this case. Okay, so let me just explain a few, to say a few words about typical workforce planning problems. You have different problems, but usually what you have in the beginning, you have some requirements you need to fulfill, which are calculated based on some task you have to do. And this red curve, which you see here, is, for example, we see that from 8 o'clock to 10 o'clock or to 11 o'clock, we need 6 employees and so on. And especially in companies like airports and so on, this can change from time to time, and it's important to reach good shifts for these cases. And then what you try to do in this kind of schedules is to generate so-called shifts. So you see here in the solution here that you have some shift A, which is a yellow one here, which starts, I think, at 6 here and goes until 11 o'clock. And you see in between some white spaces here, which are the breaks that the employee does. That means we have an employee which will take this shift, will have some breaks and so on. And you may wonder also, why do we really need to schedule breaks here? Usually you don't have so many breaks, but often in some organization you need to keep the high concentration of employees and so on, to have a regular breaks, so up to 10 breaks, depending from the shift. And in those cases, scheduling of those breaks is very, very complicated, because you want to have, imagine, for example, air traffic control. You want to have in every every time slot enough number of employees, and not too many can make some breaks in some time point. And then in the phase 3, usually what do we have is so-called assignment of those shifts to the employees. So what we see here on this schedule here is a typical workforce schedule. In this case, we have so-called rotating workforce schedule, where I see that the employee A here will work from Monday to Wednesday in a morning shift, Frühschicht in German, and then we have a Spätschicht, afternoon shift, and so on. And then employee B will work from Tuesday to Friday on night shift, and so on. Okay, so this schedule basically determines where each employee will work during the week. And what so each of those problems is pretty hard to solve. This shift design, so-called shift design with breaks, but also the assignment of shifts to the employees is a difficult problem. I will show later on the typical search space for this kind of problems. And maybe just to mention a few constraints that you can have, for example, for this problem, which is called rotating workforce scheduling. So for this problem, like I said before, you have given the shifts which have to be assigned to the employees. You have number of employees, you have the days. In this case, we have 1 week, and what you want to reach is a schedule where you assign for each employees and each day a shift or a free day, such that different kind of constraints are fulfilled. For example, of course, you have temporal requirements. On Monday, you need exactly 3 employees in night shift, or 3 in day shifts, and 3 in afternoon shift. But then you have also some not allowed sequences of shifts. For example, it's not a good idea to have a day shift after afternoon shift, or to have night shift and then free and then have a day shift. And those kind of sequences are determined, like I said, from researchers who have seen some impact on the health of employees and so on. And what is very important here is also that some sequences of shifts should not be too long. That's why you have this maximum and minimum length of successive shifts. For example, there are studies which clearly have shown that working a night shift for too long and so on can have some impact for different illnesses. So it's very important to have really good schedules in this case. So what is the problem to the end? We want to find a cyclic schedules in this case, but you can have also a cyclic schedules that will satisfy these temporal requirements, so typical requirements of the companies to fulfill their services, and other constraints which have some impact, like I said, in the health of employees, and are very important also from the labor law point of view. And of course, you can have also soft constraints like optimization of free weekends and so on and so on. Okay, so this kind of problem I showed here is called cyclic, because every employee will have the same schedule after some weeks. But you can have also a cyclic schedules, for example, for nurses in hospital, where they can also have different preferences for days in which they want to work or don't want to work and so on. Okay, and then maybe a second area where I want to go and to show some applications which are also very important regarding resource consumption, including the energy in this case, and where you also want to increase the production efficiency. And those appear usually often in industry. So here you see 3 different problems. The first one is called test laboratory scheduling problem. The second one is the oven scheduling problem, and then the third one, this is the paint shop scheduling problem. And I will just explain a bit about the first 2 problems. So what do you have here in test laboratory scheduling problem? There is a large project we had with a large company here in Vienna, which they have a test laboratory where they have to test different parts of the cars for the electromagnetic compatibility. And you can imagine that you have different rooms for testing, different equipments, employees which should be qualified for different kinds of tests and so on. So typically you have some resources which are needed for each of the tests. And usually you get different orders, which are grouped in so-called projects from different companies, and you want to finish those tests as soon as possible. And in this way, of course, to reduce also the amount of time you need for tests, but also consumption of different resources which you may have there. And of course, you have different constraints which you have to fulfill here. And this problem is also, you have related problems in literature which are called project scheduling problems, where you typically have different tasks which require different resources, and you want to make a schedule such that you have enough resources for each time slot, but also in the same time you fulfill different kind of constraints about the priority of jobs and so on and so on. In the electronic industry, you have a so-called the problem which is called oven scheduling problem, and this problem, as you see here, for this problem we have different jobs which usually needs to be grouped in so-called batches, and then they are processed in some ovens. And those ovens consume very much energy. So it's very, very important to find the right grouping of jobs and assign them to different ovens based on different kind of constraints. So for example, you cannot group all the jobs together. They have some attributes. Some jobs may need a higher temperature, lower temperature, may need to be longer put on the ovens and so on. And you also don't have available ovens all the time. You have some setup times between the ovens, between the different jobs or batches you do in the oven. So there are different kind of constraints which you have to fulfill. But if you find a very good schedule, optimized schedule, you can save pretty much energy on those cases. Other problems which have been considered in our city lab or previously include problems from steel industry, parallel machine scheduling problem, like I said, paint shop scheduling problem, and so on. And I have listed different papers to the end of those slides. So if you are interested, you can have a look on those papers. And of course, there are also listed my co-authors with which I have been working together for different kind of applications. So now, from optimization point of view, why those problems are hard to be solved is because so-called NP hardness of the problem. So in computer science, and I think most of you are computer scientists here, you know exactly what NP hard problems are. So basically, the problems for which we don't know if we can find efficient algorithms ever. So they are not in the class of problems which are solved efficiently, or P problems. And we don't know if P is equal to NP or not. But in general, we know that for this kind of NP hard problems, we have a huge search space for every problem which we have. So in this case, if we take, for example, a simple rotating for scheduling where we may have 4 shifts to assign, and we have 84 positions where we can put different shifts, then the search space will be 4 in power 84, which is a huge number. So in a best case, you cannot of course, try all these possible solutions to find the optimal one, which is maybe the best one, which fulfills the best all the constraints. That's why we need here some more sophisticated techniques, and I will say something about those techniques a bit later. Okay, another application which is now investigated in one of our projects. This is not in City Lab, but in a FFG project. Concerns the food waste reduction. So this project is called Appetite, and the aim of this project is to reduce food waste in the retail environment. And this is motivated by the current waste of food, because it seems that often the predictions for for different articles and so on are not so good. So usually you may have a bit not a great amount of articles and so on in some supermarket based on different forecasting you have. So that's why what we aim in this project is to based on sophisticated AI techniques, but also in new data and also logistic optimization to reduce this waste. And this project is in collaboration with Fraunhofer, WU Wien, and several companies like ITPS, Invenium, Kastner, Metro, and Spar, who was the supermarkets which are providing the data in this case. Okay, so you may ask here why we need again predictions, because of course there exist already different approaches to predict and in time series and so on. The point is here that what we want is to also try investigate more how to say advanced techniques in supervised learning, but also use other data. And for example, what we include in this project are also the mobile data, and also of course weather data have been also used before, but we have more features about the data which we will reconsider in this project. And regarding the input data, like I said, we already got a lot of data about products, about sales data, promotions. We have weather data, we have movement data, and of course, other data like day of the week, holidays, and so on are also very important in this case. So this project is ongoing. We don't have a final results yet. We are in phase of, together with our partners, of implementing a platform which will be able to make predictions for different articles. And but what we have done until now is the collection of the data, pre-processing, and so on, which is the phase, which is a very important phase in machine learning, and took also a pretty long time, because of course you need to put the data in such a form such that machine learning algorithms can be used. And we have also initial empirical evaluation with different techniques, and for example, automated machine learning gives pretty good predictions for those cases. Okay, so let's see now a bit some AI and optimization techniques which you can use for especially for optimization problems. And what we do in our CD lab usually is we start. So what we have seen from practice is that we have already in literature a lot of problems which are defined, well defined. You can, how to say, based on this definition, you have solved them and maybe reached better solutions. But we have also a lot of problems in industry which are not formally defined yet. So in CD Lab, we have introduced 4 or 5 new problems, which are intuitive problems and used in industry, but usually have those problems have been solved manually, and there exists no definitions in the literature for those problems. So that's why if we have existing problems, we typically, of course, go directly to the techniques here. But usually, when a new challenging problem from the industry appears, then we need to go through those steps, and to make a formal mathematical definition, we have to see what is the complexity of the problem, see what are the general variants of problems, and provide also new instances to the literature. This is also a very important point, because in this way, all the researchers are able then to compare with our methods, and also introduce their own methods for related applications. The techniques which we are typically using, or are used usually for this kind of problems in industry and also education and so on, are usually AI or optimization techniques. I will show some of them in slides later. But of course, the first part is this modeling techniques, which in a way, try to find clever models which can be solved easier by different kind of solvers. And then we have also exact techniques. In this case, we have meta-heuristics, hyper-heuristics, some hybrid algorithms, and I will also say something about automate algorithm selection and instance-based analysis, which is more technical, but I will not go too deep into details. Okay, so typically, if we have a problem from practice, which is a discrete optimization problems, like the problems which I showed from before, and you want to obtain good solutions in reasonable amount of time, the first thing we usually try to investigate are the so-called complete approaches. So what are the complete approaches? Those are the approaches which guarantee that they will find optimal solution based on some settings you put, weights you put for the constraints and so on, if they have enough time. But we know, of course, that we are dealing with NP-hard problems, and usually the search space is too large, and obtaining optimum usually is not possible for all examples, but there has been a huge progress in last years in those fields. So the first area is so-called mathematical programming, which comes from the operations research optimization area. Then we have techniques which were developed more in AI domain, like constraint programming, answer set programming, and SAT approaches. And like I said, those approaches previously have not been able to solve problems which are very large, but nowadays they are pretty good in practice, but still for some problems we may need heuristic techniques. So what we usually have to do if we don't find a good way to solve those problems with complete approaches, then we usually use some try to design some heuristic-based techniques like taboo search, simulated nailing, evolutionary strategies, memetic algorithms, and so on. I will just show some building blocks of those techniques later on. Very powerful techniques nowadays are the techniques which are the hybrids of those methods, of complete approaches and heuristic techniques, because typically you may be able to solve small sub-problems with complete approaches, and then using heuristics, you could reach better solutions later. And especially what is now a subject of intensive research are the use of machine learning approaches inside during the search, so that you can based on different components find the best way to design an algorithm based on machine learning. So in practice, usually, like I said, for complete approaches, large companies buy solvers from also different companies. And for example, in mathematical programming, the most well-known solvers or most efficient solvers, but it also depends from the problem, are Gurobi, Cplex, Skip, and so on. And Gurobi is its own company. Cplex is from IBM. And in constraint programming, you have also some very good solvers like OR tools from Google, Shaft CPU optimizer from IBM, and so on. And there is a very nice challenge called Minizing challenge, where different solvers compete with each other for different kind of problems. So every year you have results there, and usually OR tools for constraint programming is one of the best tools you can have there. And we have also, of course, answer set programming solvers, and also in our institute, there's a lot of research in this direction. So, for example, the solvers like Potasco, DLV, and so on, and also SAT solvers are very successful nowadays for solving different kind of problems. For example, we had a very good experience with high school timetabling with those SAT solvers. Okay, so I'm not going now to explain the formulas here, but if you have a look on the papers about the modeling For example, if we take the rotating buffer scheduling from which we had previously, usually in those declarative programming languages, in constraint programming, it's pretty easy to write a model, but to find a really good model is very hard. Okay, so here usually I cannot imagine that soon machine will be able to replace the humans, because you will really need new ideas to model in the right way the problem so that the solvers are able to solve it. So if you have a look on the solvers, techniques behind the solvers, usually they are based on some, so depending from the area you go, but for example, if you go in constraint programming, they are based on tree search and trying to prune parts of the search tree which may not be good for the solutions. And yeah, there are different kinds of techniques, but of course I cannot go on those techniques in this short lecture. Yeah, if we take the parallel machine scheduling problem, we have another model here, which is a MIP model, and so on. But like I said, I will skip those details about the models here. So if I have a problem which I cannot solve with complete methods, then usually I try to solve it with heuristic techniques. And very good techniques are local search-based techniques, which are also based in a bit in the intuition that people have. So usually what we do is we find one solution, and then which is maybe not so good, and then we try to improve it by small changes which we do in this solution. So we have a small changes which we'll see later, and based on that, then we may reach a better solution. And actually, local search techniques are very simple, but we can usually find very fast one implementation with local search. But finding good solutions is very hard, because you need very good neighborhoods and mechanisms to escape from local optima. But the basic structure of local search techniques is you will construct initial solution, you will generate some neighborhoods, small changes of the solution, select the best solution maybe, and then go further to step 2 again. Okay, so until you have a solution with which you are satisfied. And in literature, we have different kinds of techniques like simulate nailing, taboo search, and large neighborhood search, which include some more clever mechanism to escape local optimas. Because the main point is that with those kind of techniques, you may reach some solution, but you cannot go further because you are in this so-called local optima. And no matter what you change with these small changes, you are not able to find a better solution. So those are typical changes you can do. For example, if I take rotating for scheduling, and what the humans usually do, human planners, experienced planners, they will have a kind of schedule like you see here on the top, and try to change the shifts between each other. So those are the so-called moves, or small neighborhood relations, with which you can generate this neighborhood. And by looking in different changes you can do in your solution, you can maybe find better solution, then iteratively improve it. And those moves can be more and more complicated depending from the case. Here we have a move for finding the shortest path in TSP, for example. Here we have a move in parallel scheduling problems, and so on. Okay, so typically you have to think a lot about what kind of neighborhoods you should use so that you can improve your solution. And there is also an array of evolutionary computations where you don't start only with one solution, but you start with more solutions. And what you have here is, in addition, so-called crossover operator, which combines two solutions together. So, for example, we see that this solution here is from L1 and L2 and so on. And by combining different components of different solutions, eventually you are able to find better solutions. And combination of genetic algorithms and local search is called memetic algorithms. Those are pretty powerful algorithms. And like I said, another combinations is a large neighborhood search, which combines exact techniques with heuristics in general. But if we look for hybrid techniques in literature, in general, those are basically trying to hybridize almost everything together, what is possible or what is useful. And so you have typically the methods of AI, like different heuristics which were proposed in AI, machine learning approaches, and so on. Then you have methods of logic, methods from mathematical optimization. And the idea here is to not focus only one area, but instead to take the ideas from different areas and have then better techniques which can solve the problems in different applications. So now I'm going to show one way how to combine the techniques. For example, one of those is the so-called algorithm selection problem, which is now important to when you have a new instance to solve, to decide which algorithm you should use, and so that you spend less time and so on. And this is, of course, also from energy point of view important. If you want to have your best algorithms for a particular application. So basically, in this is not only an area of optimization problem, but also in machine learning, we have this so-called no free lunch theorem, which, if we simplify it, basically says that you have here different kind of techniques, but you don't have a technique which outperforms all other techniques in all examples. So you need, in a way, to, based on the features of the instances or problems which you are solving, to select the right technique also, and not always use only one technique. So often in practice, the people are using one technique which they know best, and then they try for all of the examples, but this is not a good idea in this case. So what is exactly algorithm selection now? You have the idea of algorithm selection is that if you are solving different kinds of problems in problem space, and you have the algorithm space, different techniques which you can use there, you want to select for a new instance the best algorithm based on some performance you want to optimize. So in optimization, you may want to optimize the time you solve. You need to solve one problem, or the objective function, and so on. In machine learning, maybe you want to optimize the accuracy or recall or whatever. So you can use different kind of performance metrics here. And the idea is that if you have some features which characterize very well your problem, you may be able to create some training data in which you see which algorithm performs well and not well in different instances based on the features which you have. And then you can learn this so-called selection mapping, which is, of course, a machine learning algorithm, which will be able then in the future to select automatically the best algorithm. So this is basically what we do in algorithm selection. And this is something you need in optimization, something you need in machine learning. So we have this automated machine learning approaches where if you have a new data set, you try to automatically find out if you should use, I don't know, random forest or neural networks, or what kind of pre-processing you should do. And all these kind of things are kind of algorithms you can use, or different methods for pre-processing on those cases. And of course, this algorithm selection methodology helps to find the best algorithm. You have additional problem here because most of the algorithms have also different hyperparameters. So we need usually some techniques which are also able to search in this search space of different hyperparameters to find the best techniques for different tasks you have to which appear in different situations. Yeah, maybe just to show here a bit how this works for algorithm selection and the way how machine learning is used here. So, for example, there was a very nice paper about using of algorithm selection for set problems. Typically what you will do here is you can create classification problem. where you list different features of the SAT problems. For example, I just listed some fictive features like number of clauses, number of variables, but you have a lot of features you can use from this particular formula. And then you let run the algorithms and you see which one is the best based on some performance. For example, in this case, which one solved the SAT problem fastest. And then you have a classification problem here. So you try to learn a model using different classification techniques, which will be able then for a new formula to predict which algorithm you should use there. You can do also algorithm selection by using regression or predicting numeric values. For example, I can learn a model for each of the algorithms, which may be able to predict for me how long it will take to run that algorithm if I get a new instance. So for example, for case of SAT problem, number of clauses, if I have 100 clauses, 80 variables, let's say algorithm 1 needed 10 seconds to solve it, and for other problems 450 and so on. I can learn here a regression model, machine learning model, which will be able then to predict for a completely new formula, which comes later on to calculate how much time do I need. So how can I do algorithm selection here is basically having those models for different kind of algorithms. I can predict very fast how long it will take, and then I just use one of the algorithms. So I don't use parallelization or whatever, but instead just select the one which is most promising to give good results for this problem. And yeah, in general, you can use, of course, from machine learning point of view, different techniques like random forest, Bayesian networks, deep neural networks, and so on. And like I said, a very, very important area now is the automated machine learning, which tries to automatize the process of selecting the best machine learning algorithm, the best hyperparameters, and also different steps in machine learning process like feature selection, pre-processing of normalization, and so on. Okay, so we have been working also in a so-called instance space analysis. So the idea is now to extend this algorithm selection to so-called instance space analysis, where you try to find out where are the hard problems and for which problems which technique work better or not. And this is applied, of course, in optimization, but also in machine learning. And this is very important also from a basic research point of view to know in practice which problems are difficult for which kind of algorithms. And in our works, we had different applications. For example, in rotatable for scheduling, what you see here in this graphic, you see with different colors, those shaft 1, shaft 2, and meta are different algorithms which have been used for this problem. And you see here, based on some features which are used for rotating for scheduling, in which regions of the features you have a better performing algorithm. So you can do here also automate algorithm selection, because if you get a new instance, you have to look where in which region of the instance space you are, and based on that select also the best techniques. And here there is another example from course timetabling, where we have used also different techniques from complete techniques, SAT like and ASP, but also simulated annealing, hybrid algorithms, and so on. And you can see here the instance space of different algorithms, which show what makes hard and easy solving of different instances. Okay, maybe in the last minutes here, I just want to say something also about reinforcement learning and the way it can be used also for this kind of algorithms which we have. So reinforcement learning is another method of learning. So it's a method where the agent here has the possibility to do different actions in each time point, and it interacts with environment, and usually it gets some reward or from the environment. Of course, if the action is good, better reward. If action is not so good, maybe a penalty. And in general, of course, there are different kinds of methods which are used here, but the idea is that the agent here learns some policy which action to apply in which situation. So we have some states, and in each of the states you can characterize with different features. And the idea is to learn this policy, which based on the future reward, predicted future reward, expected future rewards, will select the best action in a particular time point. So those kind of techniques are very powerful because they can also be used in the environments where you don't have enough training data, maybe, and you learn with the environment as you are performing different actions. So we have been developing methods, especially in hyperheuristics, which use reinforcement learning. That means you try there to construct just small components, solving components, so-called low-level heuristics. And by using reinforcement learning, you try to not implement a method which is, how to say, fixed, but you let reinforcement learning to learn which method to apply, or which component of your algorithm to apply in which stage of the search. Because what the hyperheuristics do is basically try to make the methods a bit more general. That means you have this domain barrier. You just need to provide some information about the problem representation instances and some very low-level heuristics, and the rest is a general method which can be used for different kind of problems. So those kind of methods are, of course, kind of methods which are very interesting, because eventually you could also, in some cases, perform better than experts of algorithms which try different strategies to solve the problems. But of course, here it's also very important to have a good low-level heuristic. So that's why we still need here the experts, but at least one part of this solving process can be automatized by using reinforcement learning. And yeah, you see here a typical case with hyperheuristics. In this case, the agent is the hyperheuristic. The actions are the low-level heuristics or solution components you can use in different time points. Of course, you have the problem domain, and the state is characterized with different features like last heuristic type, chain progress, and so on. And you get some rewards which are based on objective value, and the time you need to provide some improvements. And based on that, by trying it to more examples, you can learn a policy that in this situation you should use this low-level heuristics, and this was working pretty well for different kind of problems. Okay, so I come now to the conclusions, yeah, our experience is that many problems within sustainable applications are still solved manually, and there is a really huge potential to improve solutions in different domains. That's why this research, I think, is also important for those domains. And in our applications, the combination of AI and optimization was crucial. So often we reach better results by using this combination. And we had several success stories, like in test laboratory scheduling, workflow scheduling, and oven scheduling, where we could improve the solutions on those cases. Of course, there are a lot of challenges still. We still have often domain-specific solutions. So that's why providing methods which are more general, like hyperheuristics, is important in those fields. I'm always surprised that we still have problems which we cannot solve to optimality. So problems from practice are often large-scale problems, and they are getting larger and larger. And for the case of machine learning project with food waste reduction, was of course the collection of data and so on took a lot of time. So this is really a very important process in machine learning, and sometimes also the organization so on underestimate this part, but it takes a lot of time to to prepare the data in such way so that you can use the machine learning algorithm. So that's why here also this automated methods also, especially for pre-processing and so on, are also very important. Okay, so thank you very much. And if you have any questions, please go for it.
Nysret, thank you very much for your presentation. And I say the same like the last two times. I think it's like a crime story what we are hearing here in the sense of this is so, there are so many pressing problems. There are to a certain extent easy solutions, to a certain extent very difficult solutions. And I'm always asking myself, why don't we do more? But okay, at least we do the lecture. And before, just as an icebreaker question, you were just mentioning the appetite project again, and that the data collection was not so easy. No? This is general, we know that getting the right data is the most probably one of the most difficult parts. How did you deal with anonymity and privacy? When I understand it correctly, you also, of course, you have to see which food is purchased when and where, and yeah, how did you deal here with privacy and anonymity?
Yeah, I think the data here are basically about the articles, of course, and the days. So the data you saw here are about different days, how much it was sold, and so on. So basically, what the companies wanted is, of course, to what we cannot do at the moment is to publish the data sets. Okay, so we can use for our projects, but we cannot publish those. And of course, this may be if you want to anonymize the data for literature, we have to do something. We haven't done this task yet. So
okay, so it's really for I would have another question. You were talking quite a lot about this automatic algorithm selection, so that machine learning automatically is used also to find the right machine learning algorithm. Is the parameter of sustainability, of energy efficiency or the energy usage taken into consideration already when selecting the right algorithm?
I would say indirectly. Okay, so it's not so basically, of course, you can take any metrics there. So memory consumption, time it takes to solve the problem, and so on. And this is something you can put in the algorithm selection to optimize. Okay, so it's the main applications we had until now are basically based on time I need to solve the problem. And then with which technique I can reach the best solution and so on, okay? But you can extend this, and I think algorithm selection is from point of view of which algorithm to use is important to, in this case, to decide also based on other metrics, yeah? So if one algorithm takes more energy or not, and so on, but we have not been considering this, but this can be, of course, used for that too, yeah.
And I can imagine that this becomes more and more important in the future when we have to be more aware and conscious concerning our energy consumption. So I'm looking at the chat. It seems that the students are a bit shy today, although you had almost no formulas. And I would have another one more question. You were mentioning, and I think also here, educational timetabling and high school timetabling. And I really have to say, I remember my school times when there was always one teacher who had the hard job of doing this during August, so that in September we perhaps could start. Yeah? And then always there was the, every year there was the kind of the answer, there are still some kind of inconsistencies and it takes another week and another, okay. Which kind of tools are used in these millions of schools out there on the planet to do this automatically or semi-automatically?
Yeah, there exist already companies which provide such schools. For example, there is also a company in Stockerhaus, which I think has the tools in I know how many schools, but units. And but the timetable is never-ending story. We have a specialized conference only on timetabling, and there was also competition for methods to solve different timetabling problems in different countries, because you have, you know, in the school in Finland, in Austria, and so on, you have huge differences. And there are methods which work pretty well, but still there is a lot of work to be done, because you have specifics of different countries, of schools, and so on. And you have for many problems also, we don't know the optimum. So sometimes it's, I mean, of course, maybe you are not interested for just improving a bit the solution. But yeah, the things are changing, and the same is also for course timetabling in universities. So there are some solutions, but I know if we would do now for TU, for example, is not a task you can do within months, because there are a lot of specifics which are typically for TU Wien. Of course, you can use different methods in this area to solve this kind of problems, but still, you will need a lot of time for modeling and everything. Yeah.
So you were saying not for TU Wien. I was just there. I'm looking here on my second monitor. I want to congratulate you, because just on Friday the Ressel Prize was announced. Just for the participants, the Ressel Prize is kind of one of the highest dissertation awards TU Wien is providing for dissertations who have been done together with industry to solve a relevant problem. And it went to one of your students, to Lukas Gletzander. So congratulations to you and to Lukas for timetabling, but not for schools, for industry. It's perhaps easier.
Yes.
I have no idea.
Yeah, thank you very much. No, he did work in the first part, which I showed about personal scheduling, and especially in bus driver scheduling. So the breaks were very important. And yeah, he did a very good solution, but also in hyperheuristics with reinforcement learning and so on. So I was also very happy, and thank you for congratulations. I will also tell to him. Yeah.
Yeah, tell him. So I have really no further questions on my list. Now I'm looking again at the chat, and it seems there is no further question. So I would say, Nysret, thank you very much again for your very informative presentation. Thank you for all the participants for listening, and we see each other, at least virtually, next Monday for the next presentation. Thank you, Nysret, and goodbye.
Thank you very much. Yeah, bye.
Bye-bye. Please send me the slides, Nysret. Yeah? And is it okay that we put everything online, both the slides and the recording?
Yeah, no problem. Yes.
Okay, yes. Thank you very much. Bye-bye.
Bye.